Hello to all my viewers. This is Dr. Dhaval Maheta, and today we'll understand autoregressive moving average models in R. Box and Jenkins first introduced ARIMA models, the term deriving from AR autoregressive. I is integrated, MA is moving average. We'll understand ARIMA models with the help of small example. In the first column, we are having day. In the second column, temperature. The first day temperature is 75, 78, 80, 77, 82, and 79. Now we'll understand the autoregressive model first. Imagine you are trying to predict tomorrow's temperature based on the past few days. In an AR model, you will assume that the tomorrow's temperature depends on the temperature of the previous days. For instance, if the last few days have been warm, tomorrow it's likely to be warm too. The model uses a weighted average of the past observations to make the predictions. In an AR1 model, order 1, tomorrow's temperature is a weighted sum of today's temperature. So tomorrow's temperature is equal to 5 into today's temperature plus the epsilon, which is the error term. So here, phi is the coefficient and epsilon is the error term. Now let's talk about how we will run the autoregressive model. Day, today's temperature. So what will be the tomorrow's temperature? C, which is a constant mean temperature plus phi into 75 plus epsilon 1. C plus phi into 78 plus epsilon 2. C plus phi into 80 plus epsilon 3, which is an error term for the third time period. C plus phi into 77 plus epsilon 4. C plus phi into 82 plus epsilon 5. C plus phi into 79 plus epsilon 6. A generalization of the AR1 model is the ARP model. The number in parentheses denotes the order of autoregressive processes and therefore number of lag-dependent variable that the model will have. For example, the AR2 model will be an autoregressive model of the order 2 and will have the form yt is equal to phi1 yt minus 1 plus phi2 yt minus 2 plus ut. Similarly, the ARP model will have an autoregressive model of order p and will have a p lag terms as given below. So the last term is p, the moving average model. Now let's say you are predicting tomorrow's stock price. In an MA model, you will assume that the tomorrow's price depends on the combination of past forecast error, the differences between the predicted and actual values. So if the model consistently underestimates the stock price, it would adjust future predictions upward to correct for this. In an MA1 model, order 1, tomorrow's temperature depends on the forecast error from today. So tomorrow's temperature is equal to theta into today's forecast error. That is the difference between actual and predicted plus epsilon, which is an error term. So here theta is a moving average coefficient and epsilon is the error term. Same example. What will be the tomorrow's temperature? It will be C plus theta into epsilon 1. This is an error term for the day 1. This error is the difference between the actual and the predicted. So we give some weightage to this error. So C plus theta into epsilon 1 plus epsilon 2. C is the constant, which is the mean temperature. Third day, C plus theta into epsilon 2. This error, the second day error, plus epsilon 3. Fourth day, C plus theta into epsilon 3 plus epsilon 4. Fifth day, C plus theta into epsilon 4 plus epsilon 5. Sixth day, C plus theta into epsilon 5 plus epsilon 6. This is the MA model. Generalization of moving average model. The simplest moving average model is that of order 2 or the MA2 model, which has the form yt is equal to ut plus theta 1 ut minus 1 plus theta 2 ut minus 2. Thus, the implication behind the MA2 model is that the yt depends on the value of immediate past error, which is known at time t. Similarly, the MAQ model will be a moving average model of order q and will have a q lag terms as in the following. So the last term is q. ARMA models. After presenting the ARP and MAQ processes, it should be clear to the reader that we can have a combinations of two processes to give a new series of models called the ARMA PQ models. The general form of the ARMA model is ARMA PQ, where these terms are for our AR terms and these are MA terms. Now, before we understand ARIMA, that is autoregressive I. I is for integrated moving average models. It is necessary that we understand the concept of stationarity. Covariance stationarity of Y implies that over time Y has a constant mean, constant variance. Covariance between different observations do not depend upon time t, and it depends upon only the distance or lag between them, which is j. Let's understand the concept of stationarity. Plot 1. Just see the blue line. It's a constant mean. See the distance between the dotted blue line. It is constant and this is a constant variance. See the distance between the red lines. It is equal. So this is constant covariance. Remember, covariance we see horizontally, variance we see vertically. This will be much better to understand. So this is the stationary time series. Now let's talk about the second plot. Time series with constant mean. Green line is constant. That is, the mean is constant. The distance between the green dotted line is constant. So variance is constant. Now just see the distance between the red lines. It is not constant. So this is non-constant covariance. The third plot. The mean is not constant. Variance is constant. The distance between the green dotted line. And just see the distance of the red lines. So the covariance is constant. The fourth one. The mean is constant. See the green line. Non-constant variance. The distance between the green dotted line is not equal. So it's a non-constant variance. Distance between the red line is constant. So it is a constant covariance. The first example is of the stationary time series. Second, third, and fourth are the examples of non-stationary time series. We will carry out some transformations like log transformations, or we'll take the first difference of the series to make the non-stationary time series to stationary. ARIMA combines both AR and MA components, and it also introduces the differencing. Differencing involves subtracting the current observation from the previous one to make the series more stationary. So in the context of temperature prediction, you might work with the changes in temperature rather than the absolute values. Example, if the temperature data has a trend, ARIMA would first calculate the difference between each day's temperature and the previous day's temperature to remove this trend. ARIMA modeling. Now we will work on the first difference of the series. This means that this will become your dependent variable. So how we take the first difference? 78 minus 75, 80 minus 78, 77 minus 80, 82 minus 77, 79 minus 82. So the series is, we have taken the first difference of the series and it is integrated of the order 1. So the tomorrow's temperature, it will have AR terms. These are AR terms and these are MA terms. So your ARIMA model is complete. What will be the tomorrow's temperature? C plus 5 into 78 plus theta into epsilon 1, the past error. The second day, C plus 5 into 80 plus theta into epsilon 2, the past error. ARMA models can be only made on time series YT that are stationary. This means that the mean, variance, and covariance of the series are constant over the time. However, most economic and financial time series show trend over the time, and so the mean of YT during 1 year will be different from its mean in another year. Thus, the mean of most economic and financial time series is not constant over time, which means that the series are non-stationary. In order to avoid this problem and in order to induce stationarity, we need to detrend the raw data through a process called the differencing. The first difference of the series YT is given by the equation delta YT is equal to YT minus 1. If after first differencing a series is stationary, then the series is called the integrated to order 1 and denoted by I1, which completes the abbreviation ARIMA. If the series even after first differencing is not stationary, then we need to take the second differences by the equation delta YT is equal to delta square YT is equal to delta YT minus delta YT minus 1. If the series becomes stationary after second differences, then it is integrated of order 2 and denoted by I2. In general, if we difference a series d times in order to induce stationarity, the series is called the integrated of order d and is denoted by ID. Thus, the general ARIMA model is called ARIMA PDQ, with P being the number of legs of the dependent variable, D being the number of differences required to take in order to make the series stationary, and Q being the number of leg terms of the error term. So this is an autoregressive component. Yt is equal to phi into yt minus 1 plus epsilon t. The first difference is delta yt is equal to yt minus 1. Moving averages, yt is equal to theta into epsilon t minus 1 plus epsilon t. The four stages of Box-Jenkins methodology in ARIMA modeling are identification, estimation, diagnostic checking, and forecasting. Let's see the flowchart. Plot the data, identify unusual observations, understand the pattern. If necessary, use the Box-Cox transformations. You can manually select the model, or you can also use the automated algorithm, which is known as auto.arima. Step 3. If necessary, difference the data until it appears the stationary. Use unit root test if you are unsure. 4th, plot the ACF and the PACF of the difference data and try to determine possible candidate models. 5th, try your chosen model and use the Akaike information criterion to search for a better model. 6. Check the residuals from your chosen model by plotting the ACF of the residuals and doing pot-Banto test of the residuals. This you can do with the help of auto.arima also. After that, do the residuals look like a white noise? Are they stationary? Yes. Then do the calculate. Then do the forecasting. Now let's see how we can do this in R. So first of all, we will have to uh, load the data set. Our name of the data set is SenseX. Open, import. So this data set consists of date, Nifty, and returns. To run any analysis in R, it is necessary that we create script. So this can be done from here. Click on plus sign, R script. I've already done that. Attach the sensex 1. Run the command add sensex. It will generate the first 6 rows of the data. To carry out the time series analysis in R, it is necessary that we install some basic packages like T-series and ggplot. This can be done with the help of tools, install packages. You will have to go in tools, install packages, write down T-series, press install. Make sure that your internet connection is on. After that, install ggplot2. Press here, install it. Then activate its library so that you can use all the functions of T-series and ggplot2. 1, 2, plot the Nifty. You can see it is having a trend. Calculate the mean of Nifty. It is 6538.151. Plot its returns. Plot the graph of returns. Mean returns. Now, the first step is model identification. This we can do with the help of augmented Dickey-Fuller test. Our null hypothesis is series is non-stationary, or the other can be the series has a unit truth. So we'll run the test. Augmented Dickey-Fuller test, adf.test into bracket returns is equal to the alternative hypothesis is stationary 1. So here the p-value is less than 0.05. So what is our interpretation? As the p-value is less than 0.05, we reject null hypothesis, which means that the series is stationary or the series does not have the unit truth. Now let's plot the ACF of it. So 1 and 2. Now on the basis of the pattern of ACF and PACF, we will be able to predict the model. Let's see. What is ACF and PACF? Correlogram is plotted based on ACF and PACF. So autocorrelation function refers to the degree of correlation of the same variables between the two successive time intervals. So it is a correlation between yt and yt minus 1. What is PACF? Partial autocorrelation functions refers to the correlation between yt and yt minus 2, removing the effect of yt minus 1. So this is PACF. Now how it is useful? Based on the pattern in ACF and PACF, we will be able to predict that are they AR terms, MA terms, or it is a ARMA process. So if ACF is geometric and there are P significant lags in PACF, it is an AR model. In case of MA, Q significant lags, and PACF is geometric. In ARMA, both are geometric. Let's take some example. See the uh, black bar, it is of ACF. The white bar is PACF. So PACF is geometric. ACF is significant in the first lag. So what can be the scenario? Let's see. PACF is geometric. Q significant lag. So it is a MA1 process. So it is a MA1 process. As ACF and PACF are negative, therefore YT is equal to minus phi 1 UT minus 1 plus UT. Let's take the another example. ACF significant till 2 lags. PACF is geometric. So it's a MA2 process. Therefore, the equation is YT is equal to phi 1 UT minus 1 minus phi 2 UT minus 2 plus UT. The third example. ACF is geometric and PACF is significant till the first lag. So what can be the scenario? This is the case of ACF is geometric and PACF P significant lag. So it is a AR process. So it is AR1. Therefore, the equation is YT is equal to phi 1 YT minus 1 plus UT. ACF is geometric. PACF significant till P lag. So it's a AR1 process. So let's see now what is our interpretation in our case. Run ACF. So ACF significant till first lag. PACF is geometric. So what can be the interpretation? Let's check it again. ACF is significant till P lag and PACF is geometric. Okay. PACF is geometric. So it's a clear case of MA processes because Q significant lags are present in ACF. Okay. This is according to the choreogram. Now let's do the model estimation. ARIMA returns C100. So the first term is for uh, this is a ER term, this is differencing, and this is MA. So we have specified 00. It means that we are running only AR processes. 1. So we get the coefficient of AR1, we get the log likelihood, we get the Akaike information criteria. Okay, the model selection will be based on Akaike information criteria. Lower the better. The model which has the lowest AIC is the best one. Now we will run AR2 process. ARIMA returns C200. Run. ARIMA returns 101. AR1 also and MA1 also. Run. ARIMA returns 001. So let's say this is a MA1 process. MA1 model. Run. And here also you will be able to see that in the case of the previous one, this one, we are having AR and MA terms. Now let's run this. So it's having an MA. Now we'll have to select the best model. We'll have to select the best model. So let's take the summary of this on the basis of Akaike information criteria. AR1, its log likelihood, Akaike information criteria. AR2, Akaike information criteria. AR1 and MA1, that is a third model, it's AIC, and MA1, it's AIC. Now identify the lowest. So it is for MA1. It's also for AR1, but MA1 will consider MA1 because according to the choreogram also, this is a MA model. Now we also have the automatic ARIMA. If you recall in the flow chart, we can also use the automatic ARIMA, this one. Now to activate the automatic ARIMA, it is necessary that we install forecast package. So go in tools, install packages, forecast, press here, install. After that, activate its library forecast. Auto.arima returns. So it also gives me the same thing. It is a MA model. Now we will use this ARIMA model for the prediction. So we will create the new series ARIMA.final ARIMA returns. So we have finalized the model which is 001 run. Now we will do the diagnostics checking of this model, which is done with the help of command line TS diagnostics, that is a time series diagnostics run. So all the residuals are clustered, which is good. We don't have any spikes in autocorrelation function, which is also good. We don't have, or rather there are no bars outside this blue dotted lines, which means that the residuals are not autocorrelated. Plot arima.final. So this is the plot of inverse MA roots. This black point is inside the circle, which is considered to be the good one. It means that the estimates based on MA model are stable. Now we will run the forecasting based on this model. So arima.final is equal to arima returns C01. This we have already done it. So this is not necessary. This is not necessary. Okay. Now we'll do the prediction. So predicted, this is a name which we are giving to the new series. You can write any name here. So predicted is equal to predict arima.final. That is, using this model, do the prediction for 10 days ahead. N dot ahead is 10 days ahead. Run predicted. And we got the prediction for next 10 days. Now let's do the interpretation of the model also. What was our model? Just what is the model which we had finalized? Yeah, this model. MA1, this model. So let's do the interpretation of this model. Just a minute. Yeah, here it is. So YT is equal to UT plus theta 1, UT minus 1. Returns is equal to 2.5046, which is our constant. This one, the intercept. Here is it. And this is the coefficient of MA1, so 0.0654. I'll just write it down here, 0.0654 into UT minus 1 plus UT. So if UT minus 1 increases by 1 unit, the expected return would increase by 0.065. We do the small correction here. Assuming UT stays the same. So this was all about how we can run autoregressive moving average models in R. For more videos on econometrics using R, kindly subscribe to my channel. You can also refer my playlist in which I have uploaded videos on data science, machine learning, and artificial intelligence. Please don't forget to like and share my videos. You can also join me on different social medias, link given in the description box.